Hey, this is Brock Lemire's Embedded Systems Design. We are looking at the I2C peripheral on the MSP430. In this video, we're going to look at an example program of how to read from a specific register address on an I2C slave. And this will require us to use two separate messages. The first being a message to set the register address, and the second being the read from that address. Okay, so let's take a look at what we're trying to do. We are going to send two messages. We are going to do a write in order to set the register address that we want to read from. We are using the real-time clock Adafruit device that we've been using in prior examples. Its hard-coded slave address is 68. And so what we're going to do is the first message will be start, slave address 68, write, and then it will acknowledge saying I'm here. And then we will write 03, which happens to be the minute register. So we'll be able to see the second register. We'll be able to see it go tick, 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 tick every second. It will acknowledge, then the master will stop the first message. Then it will start a second message, which will send out the slave address, but this time do a read. When it does that read, the slave will acknowledge, and it is in a mode where it knows that it is supposed to send out the information from address 03. So it will pump out this piece of information that corresponding to seconds. And then the master will say knack, indicating that it has received indicating that it doesn't want any more data. That will stop the slave from transmitting, and then it will send the stop bit. Okay, so let's take a look at the hardware setup. As always, here we go. I got my MSP430. I'm using the B0 I2C peripheral, which comes out on port 1, bit 2, and 3. And so clock and data come over to the real-time clock. I also have to provide power and ground. So I've got my 3.3, and my ground coming over there. I'm going to observe the packets or the messages with the analog discovery logic analyzer channel. And I'm going to use channel 0 for the clock, channel 1 for data, and I have my little simple probe right there. If you don't know how, or if you want to make this setup and haven't seen the prior videos, go back a couple videos and I'll show you how to make that. Okay, so let's take a look at the setup for this system. Here is the I2C peripheral. As always, we're going to start by putting it into software reset so that we can set up its configuration bits. We're going to be the master, so let's go ahead and set a 100 kilohertz clock. So what we're going to have here is SM clock, and then we'll do a 1 megahertz prescaler of 10 to divide it down by 10 to get 100K. And then we'll set this up. Of course, we'll do UC mode. We'll put it in I2C. UC master, we'll set it as the master. UCTR, we're going to leave that for now. We actually need to switch back and forth between transmit and receive, or read and write, because we need to send two messages. So we're going to do that in the main loop, and you'll see it here in a second. I2C slave address, we are going to have 68 as our hard-coded value, of course. That's a real-time clock. And now what we need to do is figure out the data transmission and stop bit. We are going to have two separate messages that each send 1 byte. We can simply set the byte counter to 1, and that will always send 1 byte, either read or write 1 byte in each message. So we only need to set that up as 1. And then if we do the automatic stop bit, the system will automatically pop out the stop bit after that byte has been read or written, okay? All right, of course, we just got to switch over the port function selects to use the I2C lines instead of the ports, and then we'll take it out of software reset and we'll set up our messaging. We are going to do this manually in conjunction with interrupts. So we're going to have a main loop, and what we'll do is we'll start the first message, which is going to be a write. So we'll manually set the STT bit in the main loop, and then we'll use delay loops to kind of space them out. So what's going to happen is we'll start one message, and then we know that that is going to be a transmit. We actually have to set it into transmit mode and manually assert this bit to start a message. That'll start the message. And then what happens is it'll go out, send the start bit, send the slave address, then an interrupt will fire because we're in a write message, and it will fire the transmit interrupt. And then we will dump the information that we want to put or want to write in the interrupt service routine. In that situation, we will send out hex 3 because that's going to be the address that we want to write. And then what'll happen is that after it sends that, the slave will act and the system will automatically send the stop bit. We'll have a little delay loop to space out so that in between the first message, And then what we'll do is we'll send the second message, but in that situation, we have to put the transmit bit to receive, which means read, and then we'll manually assert the STT bit again, and that will start the second message. And then in that situation, what'll happen is it'll send the start bit, send the slave address, send the read signal, and then the slave will send back the information at register address 3. When it arrives, it will trigger the RX flag, or the receive 0 interrupt. We can then go into the interrupt service routine and grab that information. Now the trick here is once we grab it, we know that we're done because we've grabbed 1 byte. So the byte counter's at 1, so that automatically triggers a stop. But since it also is at 1, the master knows it's done reading. So it goes ahead and sends a NAC automatically, and that tells the slave to stop sending us information, and then it sends the stop bit. Now here's the trick here. We got 2 interrupts. We have 2 pieces of functionality that we need to code in one interrupt service routine. So we have to have a way to determine what caused the interrupt service routine. So it could have been the transmit or it could have been the receive. Let's go ahead and use the interrupt vector to do that. This will be the first time we've used the interrupt vector code, and that'll give us a chance to actually see how this works. Okay, holy moly, this is going to be probably the most sophisticated program we've written to date. So let's go ahead and fire up a new CCS project, and we'll go ahead and call this C underscore I2C underscore RX2. It is a receive, and we're going to do master read from reg ADR. Okay. We are going to do a write message and a read message, but ultimately what we're trying to do is read from a specific address. So we want to, or a register address. So we want to put this, I want to call it read something. Okay, here we go. Ready? First thing, let's put it into software reset. Okay, and we're going to do that by going to the UCB0 control word 0 register. And we are going to set a bit using a bitwise OR, and the mask is UC software reset. Okay. All right, there it is. I'm going to go ahead and grab this register name because we're going to use it a lot. I'm going to copy that. All right, now we're ready. Let's go ahead and choose SM clock. Okay, so we'll go here and we'll go into this bit or into this configuration register and do a bitwise OR with UC SSEL underscore 3. That mask will choose SM clock. Okay. All right, next one is we are going to set prescaler equal to 10 to divide down SM clock in order to get 100 kilohertz. So that is in the UCB0 BRW register. And all we do is drop in 10. So that's the bit rate register. Okay, so that's the clock setup. Now let's put into I2C mode, and that's done in the same register here, control word 0. And what I want to do is I want to bitwise OR to set the UC mode underscore 3 mask. So that's going to put it into mode 3, which is the I2C. Modes 0, 1, and 2 are SPI. Okay, now let's put it into master. So let's put into master mode. And we'll do that by going into the same configuration register, and we will bitwise OR it with a mask called UCMST. So that puts it into master mode. And then we can do the slave address. So we're going to do, let's see, slave address equals 068, and that's the RTC. Okay, so that's our hard-coded slave address. And so we set that by going to the UCB0 I2CSA, and I'm just going to drop that in there. It's 0x68. Okay, notice all these configuration registers, it's the B0, UCB0. That's how I tell that I'm setting up the B0 peripheral. Notice at this point, this is usually where we do the transmit bit mask, so whether we're going to read or write. We're not going to do that right now, okay? So we're going to do that in the main loop. So the next thing we're going to do is byte counter equals 1, because each message will only send or receive 1 byte. So I go out to the UCB0 TB CNT, and I'm just going to drop a 1 into there. And then what I want to do is in conjunction with that, I want auto stop mode. And auto stop mode is actually the only bit in the control word 1 register. And what I want to do is I want to set the this mask right here. It's called UC auto stop _2. In that particular mode is going to say whenever we have either read or written the number of bytes in byte counter, I will go ahead and automatically generate the stop bit. And it's done automatically, so that's awesome. Okay, so at this point, the peripheral is pretty much set up. So now we can go ahead and set up ports. Remember, we need to, the first one is we want port 1 bit 3 is equal to SCL. Okay, and that is, let's see, so we got to go into the port 1 function select register. That's port 1 SCL. We're going to clear the most significant bit by doing bit 3. Okay, and then we'll copy and paste a little bit here to so that our spelling is right. And then we go into port 1 select register 0. So that's the other register that works in conjunction. There's 2 bits we need to set, or set and clear. So then we have 0, 1 on port 1 function select 1 and 0, those 2 registers in bit position 3, and we set 0 in this field, and then we put a 1 in that field. Okay. All right, so that's good. That's good. That looks good, I think. And now we'll do this. Copy and paste it, and let's set up the data. So port 1 bit 2 is going to be SDA. Okay. And then what we do there is that is bit 2. So all we need to change is the mask for bit 2. Okay, so that's good. And now the last thing is we need to turn on the I/O system by taking it out of low power mode. So I go to power module 5 CTL0 and I clear the lock low power mode 5 bit, and this turns on I/O. Okay, so now let's go ahead and take it out of software reset. So I go up here, I'm going to grab this code right here. Thank you. And I didn't put my comment of that I usually do. Setup B0 I2C. Okay, so then I come down here and take it out of software reset, and I do that by clearing this bit. So whenever I clear, I do ampersand equals tilde and get my comment there. So I take out of software reset. All right, life is good. Now we are ready to roll here. What the only problem, or now we're pretty much set up with our peripheral, but we need to set up some interrupts. So set up IRQs, and we are going to have 2 interrupts. Now this is interesting. We are going to have 2 separate interrupts that we enable, but both of them share the same vector address. So we are going to enable in this register UCB0IE. That's the configuration register that holds all the local enable bits or for all the interrupts that you can have. And remember, with I2C, there's a ton of them. There's like 16 separate interrupts that you can have. We are going to enable the UCTX-IE0. So that is the TX IRQ. And that one is specifically operates where in a write message, when you send the start bit, slave address, and the write signal, and the slave acknowledges, this will fire, indicating to us that the transmit buffer is ready. The next one we are going to do is UCB0IE, same configuration register, but it's the UCRXIE0, and that is the RX IRQ, and this one operates when you are in read mode, and after you send the start bit, slave address, read bit, the slave acknowledges and sends back the byte of information. Once it has been received, this interrupt will fire and indicates to us that the receive buffer is ready to be written. Okay, so we got 2 interrupts, and we'll go ahead and enable interrupt. And this goes ahead and enables the maskables, the global interrupt. Okay, and so at this moment in time, we're feeling pretty good, and we're ready for the main event. Okay, half of the main event. Because we got to use the main loop and also the interrupt service routines. So we got it with a lot of stuff going on. Okay, number 1. We are going to start with a infinite loop. Okay, we're going to continually do this. So I'm going to go while 1. Okay, and I'm going to go ahead, and here's my main loop. All right, in here I've got 2 kind of pieces of functionality. The first one is transmit register address. Okay, with write message. Okay, so that's kind of the first big piece of functionality. Then we're going to do some logic for that, and then just to show the second big block is we're going to receive data from RX, receive data from slave with a read message. And this is pretty awesome because we're going to be using the main loop and interrupt service routines kind of back and forth it is. Okay, so let's start. Let's just think through the transmit. Okay, so here we go. I need to transmit the register address. So I'm going to go in and I'm going to go to the UCB0 CTLW0 register, and I am going to put it into transmit mode by bitwise ORing it with UCTR to set that bit. Okay, so now I'm sitting here and put into TX mode. Okay, so now I'm in transmit. Now let's start a message. So I'm going to go to UCB0 CTLW0 and I am going to bitwise OR it with UCTX STT. So this generates start. Okay, now here is where we're at. Think about what's going on right now. I've started a message and it's going to send out start bit, slave address, and write automatically. Then it's going to trigger an interrupt and it will then say, hey, we're ready to transmit and I need to put something in the transmit buffer. But I'm going to put the information in the transmit buffer, which is address 03, in an interrupt service routine. So then what I'm really doing in the main loop is I'm waiting for the message to stop. Okay, and I could very well do a delay loop here, but we're kind of getting sophisticated. So why don't we monitor the flag? So let's monitor the flag to know when this message is done. So I'm going to do a while loop. So check out this logic. I'm going to do a while loop, and I'm going to sit in this while loop as long as the following condition is true. I'm going to look at the stop flag, and when it is equal to 0, okay, when the stop flag is equal to 0, I will stay in this little loop, and only when the stop flag has been asserted will I come out and proceed to do the next things. So here's the logic for the stop flag. The stop flag is, the mask for it is UC STP IFG. Okay, so that's a flag. But remember, that's a bit mask of a bit position in a register. So the register that this flag resides in is UCB0 IFG. And so what you do is you do a bitwise AND. Okay, and so what happens is that if this flag right here is 0, this bit position, remember this is going to have a bit mask of like 00000001000, and that 1 corresponds to the position where this stop flag is. And so when you do this bitwise AND, this is a logical AND, Boolean AND. It's not a bit set, bit clear, it's a Boolean AND. And so it clears all the bits except for this stop bit. And then since it's 0, it's going to be 0. And then the only time that it's not 0 is when the stop flag is asserted and this condition becomes false, and you will leave the while loop. So this is it's a poll. We are essentially polling the stop flag to just wait for the message to be done. So then when it gets done, let's go ahead and clear the stop flag. Okay, so we'll go ahead and do UCB0 IFG, and this time what we're going to do is we are going to clear that by doing UC STP IFG. And so then I go ahead and I clear the stop flag. Okay. And the reason I did that was because I want to get ready for the next message. Okay. Because we want to get ready for the next message. Okay. So here we go. Now I'm ready to start the next message. And here we are. Okay. So here we go. And so I'm down here. And now what am I going to do? Well, if you think about it, a lot of this is going to look very similar. So I'm gonna copy this entire thing, and the only difference becomes this. Instead of putting into write mode, we are going to put into read mode. So what we need to do is clear this bit. Okay, so we go ampersand equals tilde. We still generate the stop bit. So generate the start. So the start bit is generated, and then we again come down here and wait for this message to complete, and then we go ahead and clear the stop bit, and then we are now officially done with our infinite while loop here. Okay, so those are the two pieces. Okay, so now that's the main loop. Okay, that's the main loop, but we still have not written the interrupt service routines. We need an interrupt service routine that when the transmit IRQ fires, we need to put information in the transmit buffer. And when the receive information the receive interrupt fires, we need to read from the receive buffer. Okay, so we got a little bit more to go here. So we need to come down here and do our interrupt service routines. Okay, so ISRs. All right, first and foremost, we're going to write one interrupt service routine because there's only one vector. So I need to go pragma and tell the compiler, hey, I need to set up the interrupt vector for EUSCI underscore B0 underscore vector. And go to that vector address and put the starting address of the following routine. Okay, so I'm going to do, it happens to be an interrupt, but here's the name of the routine I'm writing. EUSCI, and I'm making this up. This is what I'm writing this out. ISR and void. So I'm sending it nothing in, I'm getting nothing back, and it is an interrupt, so it needs to return with RETI instead of RET. And now we're sitting here, and this will fire when both the receive and transmit flags are set. And so I need a way to figure out which one I'm looking at. So I'm actually going to use this interrupt vector for the first time. So the interrupt vector is UCB0IV, okay? And I'm going to do a switch statement. So I'm just going to look at the value here. I'm going to say UCB0IV, and I go look in the data sheet and I see that there's specific codes that exist within this register that represent which flag was raised, okay? And so I can do the following. I can come down here and say case, and I go look up in the data sheet, and it turns out that 0x16, this is the ID 16, is the RXIFG0 interrupt. And it's like, that's awesome. Okay, that's awesome. So if the receive fires, okay, what do I want to do? Well, I'm going to do something, okay, and I'll come back to that in a second, okay? And then after that, I will break. Okay, I'm just setting up the cases right now. So then let's do that, yeah. So then if I have a case of another code, which happens to be 01X, this is the ID, ID is 18, and that means the TXIFG fired, okay? And so then here I'm gonna do something, and then I will break, okay? So these are the two codes, and I got this from the data sheet. I went up to the Monster User's Guide, and I said, tell me how this interrupt vector works. And I said, well, if you ever see the code 16, that means RX flag was raised. And if you ever see 18, then the TX flag was raised. And I can put this, you know, it probably makes more sense to do the transmit first, but yeah, that's fine. Then what do we need to do in the default condition? Okay, so the default, I'm not going to do a dang thing. I'm just going to break. So any other code, I got to get out of here. Okay, all right, so there's the shell for deciding which interrupt is fired. And now what I need to do is write the code. So now let's think about what am I doing? Let's do the transmit because that's the first message we're handling. What do I do if a transmit interrupt has fired? Remember, just to reiterate this, if the interrupt service routine has fired, if this transmit flag has been raised, I have sent the start bit, sent the slave address, sent the write bit, the slave has acknowledged, and then it fires and says, hey, put something in the transmit buffer because I need to send it. So I need to put in the transmit buffer something. Well, remember what we came to do here. What did we come to do? What is the whole point of this program? It is to read from address 03. So I am going to send at this moment 03. So that's what I'm doing. Send reg address. And then I break, and that's it. So I will send that address. Awesome. Okay, now let's think about this. Now if this one fires, the receive flag has raised, what am I trying to do? Well, I am trying to receive whatever information is coming from the slave that just was put in the receive buffer. So what I need to do is read the receive buffer. So I'm going to make a variable called data in. I need to set this up, obviously. And I'm going to read from the RX buff. So I go ahead and I read data from RX buff. And there it is. And so now I'm sitting there and I'm like, boy, that's pretty cool. So here is my switch case logic. And then this is the interrupt service routine. So I'll bring that up there. The last thing I need to do is I need to set up a variable called data in. So let's do that as a global just so that we have a better chance of seeing it in the debugger. So this is an 8-bitter, so we'll do car and then data in. And holy cow, we are ready to we are ready. So we can do data in is equal to 0, or you can just leave it. Okay, holy moly, let's go ahead and compile this. We must have a billion typos in here because we were going so fast. So let's go ahead and clean these buddies up. So the first one is at 54, expecting something. So line 54 expected a colon. Oh, not line, error 54. It's line 71. Okay, so come down to 71. Oh, yeah, there we go. Yeah, you got to have the colon with switch case. Come on. All right, so go ahead and save that. Go ahead and fire this up. One more error. Let's see where we got her. So come down here. And now we're at line 75, expecting a semicolon. What are you talking about now? Semicolon. Oh, yeah, you got to put a semicolon there. Come on. All right, so we got that. Let's clean that, buddy. It's getting through kind of toward the end there, so it must be getting close. Holy. All right, here we go. Here we go. All right, so this is crazy. So I'm going to go ahead and run this, and who knows? Something might be happening. So let's go ahead and fire up a logic analyzer. And here's my logic analyzer. I've got waveforms. Waveforms is a tool that I use to connect to the analog discovery. And I'm going to go ahead and add some signals. So I go ahead and add I2C. Data, clock is on channel 0, data's on channel 1, address is 7. Give me the information in hex. Go ahead and go that. Set up the pulse or the trigger to be protocol. Trigger when you have a start bit and go ahead and run. Oh my goodness. There is a lot of information happening here. And oh baby. So we have so much information going back and forth. I'm seeing it flip back and forth between read and write. So we need to set up a trigger to like try to lock this down so I can actually see what's going on. So logic analyzers are very powerful when you get to the point where you have like protocols going by. So we can actually set up a trigger that will look for a very specific thing. So go back to protocol I2C and let's set up a little bit trigger that's a little bit more advanced. So what I want to do is I'm changing the trigger to address and data. So I'm actually going to look for a specific address. And so type into here 0.68, okay, or 0x68. And so it's going to look for 68. And then it can say, are you reading or writing? So let's do the write. So what this does right here is it says, if it ever sees a write transaction to 68 and there's an acknowledge, go ahead and trigger. And that will be t equals 0. And what that's going to do, if I hit OK, what that does is it puts at position 0. So go up here now and go to position 0. And then it will trigger when it sees a write to that address. And now you're sitting here and you're like, oh my gosh, this locked down. This is pretty cool. I want to zoom in and try to get just a little bit more zoom in here. But if I use the scroll, the control scroll bar, it just zooms in too much. So I'm going to type this in manually. I'm going to type in 75 microseconds per division. Let's go to 50 and see. Okay, so there, can I get 2 on the screen? Okay, holy buckets. Look at what is happening right here. This is the first message, okay? I'm writing 03 to a slave. And there's the start, there's the ACK, there's the NAC right there. You can't see it. Well, no, you get it. You get NAC. And then here's the read. Look at what's coming back from the slave. The number is changing. What is that about? You know what we're doing? We are reading from register 3 in the real-time clock slave. That happens to be the second field. It is counting 1001, 1002, and guess what's going to happen? It's going to go 59 and roll back over. Boom. This is counting. This is unbelievable. So this is sitting here counting. This is awesome. What would happen if I went and read from 04, do you think? We would be looking at the minutes. Now, it wouldn't be as exciting because it would take 60 seconds to roll over, but this is unbelievable. You actually did this. You did it. You know what is even cooler? Nothing. Okay. You have done the most sophisticated program of this book yet. So congratulations. Holy cow. I know that took a long time, but I think you can agree it was worth it. Yes. All right. So as always, remember, support the channel by subscribing and see you.